Okay, so this lesson is all about some exceptions to the octet rule and how that affects Lewis structures. And then we'll talk a lot about bond order, bond length, and bond strength, and the factors that affects that, and we'll do some calculations with that. So first of all, two exceptions to the octet rule that are easy to talk about and get through. The other one will be a little bit more involved. First of all, the boron compounds, where any compound where boron is in the middle of the compound, sometimes, not all the time, but sometimes will not follow the octet rule. It will stop once it has 6 electrons, okay, forming 3 single bonds. So the typical example of that is a compound like boron trifluoride, right? So if you do your electron count, all these fluorines have their octet, but the boron only has 2, 4, 6 electrons, and it's happy with that. So another exception to the octet rule is free radicals. Now, we don't talk a lot about free radicals in this course, but you may be familiar with it. You've probably heard the term antioxidants, like, if a food is rich in antioxidants, or you take a nutritional supplement that has antioxidants in it. Well, those are meant to combat free radicals, because a lot of the metabolic processes that go on in your body will generate these free radicals, things like UV radiation and other types of radiation. Ionizing radiation create free radicals also, and those can damage your DNA and things like that. And so that may be the context in which you've heard it. So free radicals are very reactive because they don't obey the octet rule. They have an odd electron count, and so they're going to have an unpaired electron. And in general, electrons don't like to be unpaired. There's important exceptions to that, but that creates a species, a chemical species that is very reactive. And so a good example of that is nitric oxide, NO. So if you do the electron count, you got 5 for the nitrogen plus 6 for the oxygen, totaling 11. And so if you were to draw the Lewis structure for that, there's no way around it. You have to draw an unpaired electron on it. And so it might look something like this. Okay, so those are the two easy to talk about exceptions to the octet rule. So the one that we're going to spend more time on is when you exceed the octet. So the way you do that is by expanding your valence shell, and the key ingredient, if you will, are the d orbitals and f orbitals too, although we won't get that far into the weeds to discuss anything with electrons and f orbitals. But as we know, the octet rule comes about from filling up the s subshell and the p subshell, 2 in the s, 6 in the p. But if you have an atom that has d orbitals, and remember that's based on its position in the periodic table, okay? So for example, sulfur hexafluoride, sulfur is in period 3, so it can have the 3d subshell, and so it can accommodate more than 8 electrons in its valence shell, and that's what's going on here with this compound, sulfur hexafluoride. So if you do the count on the sulfur, you've got 2, 4, 6, 8, 10, 12. Okay, so in this case, you've got 12 electrons on the sulfur exceeding the octet. So as we already said, there's a couple instances in which this occurs routinely. First of all, if you have a compound with strongly electronegative elements like fluorine, oxygen, or chlorine, so as you can see in the example that we provided, that one of the elements in that compound is fluorine, highly electronegative. Okay, so that's one situation to look for it. But another requirement is that you have to have, pardon me. So there's one other reason why it would do this, and that is to decrease formal charge on the central atom. Okay, so the reason why it would exceed the octet is to lower that formal charge on the central atom. Okay, and of course, what happens in this situation is that you're exceeding that bonding capacity that you normally would attribute to that compound based on its position in the periodic table. So it breaks the rules regarding bonding capacity. So on lesson 1, we talked about sulfur. If we follow the Lewis symbol model, you would end up with 2 unpaired electrons. So that means that you would think that sulfur has a bonding capacity of 2, because each of these unpaired electrons would like to form a pair with something else, another atom, and therefore you think that sulfur would like to have 2 bonds. Well, a lot of sulfur compounds, sulfur-containing compounds, do have only 2 bonds. But in this situation where you have strongly electronegative elements, or to decrease the formal charge on the sulfur, you could have it exceed that bonding capacity of 2 and go all the way up to 6. It can have a bonding capacity of up to 6. All right, and so I thought it would show up on the slide, so I'll just mention it. But again, the other requirement is you have to have those d orbitals available, which only occurs in periods 3 and below. So some element that's in period 3 or below, because you have to have the d orbitals in order to exceed the octet. Okay, so I'll do an example here. So we're going to draw the Lewis structure for selenium tetrafluoride. So in this case, we're just going to follow the step-by-step. So it's just the same step-by-steps that you've used up to this point. But now we're just not going to care if we go past 8 electrons on the central atom. So the first step, of course, is to calculate the total number of valence electrons. And so selenium it's right below sulfur, so it has 6 valence electrons for the selenium. But then each of those fluorines has 7, but I got to multiply that times 4 because there are 4 fluorines. Okay, so 4 times 7 is 28, plus 6 is 34. So I've got 34 valence electrons to assign. And the other thing I got to do is I got to pick a central atom. Well, this makes it pretty easy because I've got 1 selenium and 4 fluorines, so I'm going to put selenium in the middle, and I'm going to put the 4 fluorines around it. Okay, and the next step says to connect all the perimeter atoms with the central atom, and so that used up 8 electrons. Okay, 2, 4, 6, 8. So that leaves me with a total of 26. Okay, and so now the next step is to give your perimeter atoms their octet with lone pairs. So I'm going to do that. Okay, so that was 24 because I've got 6 on each fluorine that I put on there times 4. So that's 24 that I just used up. And so that means I have 2 left over. And so now, again, following the step-by-step, it says to put those 2 electrons on the central atom. So we're going to do that. Now, normally, you would maybe raise an eyebrow to that because this gives the central atom more than an octet. It gives it more than 8 electrons. 2, 4, 6, 8, 10. But now we know that's okay because selenium is something with d orbitals, right? Because it's in period 4, and we also have the other, the electronegative fluorine in the compound, so that tells us that, hey, it's likely that we can exceed the octet in this compound. Okay, so that's the Lewis structure for selenium tetrafluoride. So I'll erase that. We'll let PowerPoint take over. So the number of valence electrons is 34. Pick the central atom, put the fluorines around it, connect the atoms with the single bonds, and then we're going to use up 8 electrons in doing that. There they are. So now we're going to give each perimeter atom an octet with lone pairs. So that's going to use up 24. There they are. So I've got 2 left, and it says in step-by-step to put those 2 on the central atom. So now every atom has an octet, so place the remaining 2 electrons on the central atom, and there they are. Okay, so there's an example of exceeding the octet and how you do Lewis structures for these kind of situations. Okay, so we're just going to do a couple more examples just to kind of drive home the point. So first of all, we'll do phosphorus pentachloride. Okay, so the number of valence electrons here is we've got 5 for the phosphorus, and then we have 7 for each chlorine, and there's 5 chlorines. Okay, so that's a total of 7 times 5 is 35, plus 5 is 40. Okay, so I'm going to pick a central atom. Well, I'm going to put phosphorus in the middle. All right, and then I just got to put the 5 chlorines around it. Okay, so the next thing I'm going to do is I'm going to connect all those with single bonds. All right, so that used up 10 electrons to leave me with 30. Each bond is 2 electrons. And so now I give each perimeter chlorine their octet with lone pairs. Drawing lone pairs is the tedious part. Okay, so in that case, I just added 6 to each chlorine, right? 2, 4, 6, and I did that 5 times, so 6 times 5 is 30. So I used up all 30 of my electrons. Now, everybody has, or pardon me, all the electrons have been assigned. all of the chlorines have their octet, and then if you count electrons on the phosphorus, the central atom, you have 2, 4, 6, 8, 10. So once again, you exceeded the octet. You didn't need, in this case, to put a lone pair on it like we did in the previous example, but we still exceeded the octet just with these bonds that it forms with the surrounding atoms. Okay, so another one, IF3, iodine trifluoride. So the number of valence electrons here is we have 7 for the iodine, and we have 7 times 3 for the fluorines. So that's a total of 28, essentially 7 times 4, right? And so I have to pick a central atom. I have 1 iodine, so I'll put that in the middle, and I'm going to put the 3 fluorines around it. And then I'll connect those atoms together. So that used up 6 electrons, 2 for each bond. So I have 22 left. And so now I'm going to give the fluorines their octet with lone pairs. Okay, so that used up 2, 4, 6 times 3, which is 18. Okay, so I use up 18 of the 22, so I have 4 electrons left over. And so now again, the step-by-step tells me to put those lone pairs on the central atom. So put them on the iodine. Okay, and so now the iodine, if you're doing your electron count, you got 2, 4, 6, 8, 10. So once again, you've got 10 electrons around that iodine in this compound. Okay, all right, so let me erase all that. You can get to see it nice and pretty with the PowerPoint. Okay, so the phosphorus pentachloride, there's all the electron count. The iodine trifluoride, okay, so it's just, where you put the lone pairs is not as important. So this Lewis structure looks a little different in terms of the placement of the fluorines and the lone pairs. We'll get into the important part about that next week. Okay, so that's how you do it. Okay, so the next thing I wanted to do was to go over a couple problems in the extra practice assignment in Chem 101 to show you how the Lewis structure that you come up with sometimes depends on your goal, and that will have an impact on whether or not the central atom exceeds the octet. So we'll look at questions 14 and then 46. It involves the same compound, but 2 different goals. So in 14, it says that we want to draw the Lewis structure where we ensure that we follow the octet rule on all atoms. So we're going to start with this skeletal structure, and then we're just going to finish it with electrons so that it follows the octet rule on all atoms, okay? So the first thing we're going to do is follow the step-by-step process, and that means that we need to determine the number of valence electrons, okay? Just like every other Lewis structure. Okay, well, we have 6 for the sulfur, and then each of those oxygens also have 6, and there's 2 oxygens. And then each of those chlorines has 7, and there's 2 chlorines. So that's 6 plus 12, which is 18, plus 14, which is 32 electrons, okay? So we already put the sulfur in the middle, put the other atoms around it, and connected the sulfur to each of those atoms. So that used up 8 electrons, 2, 4, 6, 8. So I can subtract 8 from the total, okay? And that gives me 24 electrons left. So now the next thing to do is just to, if you're following the step-by-steps, is to put an octet on all these perimeter atoms with lone pairs. So that oxygen gets 6 electrons, that oxygen gets 6 more electrons, that chlorine gets 6 more electrons, okay, and that chlorine gets 6 more electrons, okay? So if we do the count, that used up all of our remaining electrons, okay? So I just did 6 times 1, 2, 3, 4. So 6 times 4 is 24, so I just used up all of my electrons. So I'm done. Everybody has an octet. The sulfur has its octet also, 2, 4, 6, 8. So if I'm trying to follow the octet rule, then I'm done. But before I scroll away from this particular presentation, let me show you, or actually we can do both things here. Show you the valence electrons here. So that has 8 valence electrons, okay? So everybody's got their octet, just like the problem said we were supposed to do. But now that we know about formal charge, let's take a look at the formal charges on all of these atoms. okay? So right now, I don't know that I've minimized the formal charge on every atom in the structure because the sulfur has a formal charge of +2. Now remember what we said in the notes just a few slides ago. It said that the reason why a central atom might exceed an octet is to reduce its formal charge. Okay, so for question 46, it says, same compound, SO2Cl2, but in this case, it tells us that the formal charges are not minimized. And so we're going to start from this structure, and we're going to tweak it so that we minimize the formal charge. Okay, so here we go. So right now, I've got a formal charge of +2 on the sulfur, and remember, that's the one that we need to lower. And so what we can do is I can make a double bond with the sulfur with one of these atoms right here. And that will bring the formal charge down on the sulfur. And the other consequence of that is that I'll exceed the octet on the sulfur by doing that. So I think what I'll do is I'll click that bond and I'll turn that into a double bond. Okay. And then remember what I did was I took one of these lone pairs from the oxygen and converted it into a bonding pair. So I need to go back to the oxygen. And I need to bring that down to 4 electrons so that I have the correct electron count. All right. So now look at the formal charges. So now the formal charge of the oxygen went down to 0, and the formal charge of the sulfur went down to 0 as well. But right now I've exceeded the octet. I've got 2, 4, 6, 8, 10. Because remember, each of these lines represent a pair of electrons. So right now the sulfur has 10 electrons. But hey, I haven't filled up those d orbitals completely yet, right? So maybe I could even reduce it a little further. And the answer is yes, I can. So what I'm going to do is I'm going to do that again with this oxygen over here, because it's still got a -1 formal charge, and the sulfur still has a +1 formal charge. So maybe I can do better by converting this double bond, or pardon me, this single bond into a double bond as well. So I'll click the bond, I'll go to a double bond, okay, and remember I got to change the number of lone pairs on that oxygen down to 4, okay, and looky there. So now everybody's got 0 formal charge, 0, 0, 0, 0, 0, okay. But in order to do that, I had to cause my sulfur, the central atom, to exceed the octet. So now the sulfur has 2, 4, 6, 8, 10, 12. 12 electrons. Okay, so now let's talk about bond order, length, and energy. And this picture gives a lot of it away. Okay, so for example, if I have this compound, C2H6, which is called ethane, all right, so their carbon-carbon bond length is 153.5 picometers, and it's a single bond. Okay, well, if I change that up just a little bit, I get rid of 2 hydrogens, and I make that a carbon-carbon double bond. First of all, it gets shorter. So it shrinks to 133.9. Okay, and it's a double bond. Okay, and then if I get rid of 2 more hydrogens and just make, this is called acetylene, okay, like acetylene torch. This is the compound that's burning in an acetylene torch. So in this case, you've got a carbon-carbon triple bond, and it gets shorter. So it went down to 120.3 picometers. Okay, and the other thing we're going to see is that as the bond order increases, we go from single to double to triple, not only does it shrink, but you're going to see that this bond gets stronger. So a double bond is stronger, harder to break than a single bond, and a triple bond is stronger, harder to break than a double bond. So that's the general rule. So these covalent bonds, they get shorter and stronger as they increased in bond order. Okay, and here's a nice table with a couple pieces of information for a lot of different bonds. And so, for example, this first entry here, carbon-carbon single bonds on average. So this table is a table of average values. So there's lots of compounds in the known universe that have carbon-carbon single bonds in them. So on average, those bonds are 154 picometers in length and 348 kilojoules per mole in bond energy. Okay, so that's what this represents. This is not for a particular compound, and it changes from compound to compound. But on average, these are the values that you could see, and it's very useful. As you'll see, we can use table values like this to predict a lot of energy changes in reactions and also structural features in compounds. All right, so we're going to focus, though, on the bond energy part of things today.
Excuse me?
Okay, so first of all, what do we mean by bond energy? So by definition, it's the energy needed to break 1 mole of covalent bonds in the gas phase. All right, so again, all these numbers are for the gas phase.
Are you mental?
All right, so a couple important things about bonds. First of all, if you're going to break a bond, that's going to consume energy. That requires the input of energy. It is an endothermic process. But then when you form bonds, that's going to release energy. That drops the situation down to lower energy. So all these bond energies, if I were forming these bonds, so if I was forming a carbon-carbon bond, that would be negative 348. So if I'm breaking a carbon-carbon single bond, it's positive 348. If I'm forming a carbon-carbon single bond, that's a negative 348. So breaking bonds consumes energy. Forming bonds releases energy. Okay? And so that is very helpful if you have a table, because you can just use those bonds, those bond energies, and this equation to estimate, that's a key word, estimate, the enthalpy change of a reaction, just like we talked about in week 3, I believe it was, with thermochemistry. We talked about those enthalpy changes of a reaction. And so you can estimate the enthalpy change of a reaction if you have a table of bond energies, and you are also have the reaction. Okay, it's going to be, you add up all the bond energies for the bonds that you're breaking, and you subtract from that the sum of those bond energies that you're forming. Okay, so for example, let's say that I have this reaction right here. This is the combustion of methane. So CH4, methane. If I'm going to burn it, it requires 2 oxygen molecules, 2O2, or 2 moles of oxygen. So a mole of this requires 2 moles of this, or I can think of it just on the molecular level. A molecule of this requires 2 molecules of this, and it produces 1 molecule of CO2, carbon dioxide, and 2 molecules of water. So I know from the table those average bond energies. The average bond energy for a carbon-hydrogen bond is 413. The average bond energy for oxygen is 495, O2. And then the average bond energy for OH is 463. And the average bond energy for a carbon-oxygen double bond is 799. And so if you think about it, there's 4 carbon-hydrogen bonds in methane that I need to break. I got to break those bonds in order to form these products. And I have to break 4 of them. So 4 CH bonds, each one of those is going to cost me 413 kilojoules per mole of energy. And I've got 2 oxygen molecules that I got to break apart. And so there's 2 oxygen-oxygen double bonds that I have to break. And so each one of those is going to cost me 495 kilojoules per mole of energy. All right, so those are the processes of where I'm going to break bonds, and therefore it's going to consume energy. But then when I form these products, I'm going to be forming some bonds. I'm going to form 4 OH bonds, okay? 2 water molecules. Each water molecule has 2 OH bonds, HOH, right? So there's a total of 4 OH bonds that are formed when I produce these 2 water molecules. And so that's going to release, or negative 463 times 4. And then I'm also going to form a carbon dioxide molecule, and that has 2 carbon-oxygen double bonds. If you were to draw the Lewis structure for this, you would see that it's got 2 carbon-oxygen double bonds in it. And so that's going to release 2 times 799, okay? So this is just talking through it. I'll actually do the calculation in a slide later, but I also want to show it to you in a picture, just to kind of, again, illustrate what we're doing so you conceptually understand what we're going to do here. So I'm going to take a methane molecule and 2 oxygen molecules, and essentially what I'm going to do is I'm going to break all of these bonds. I'm just going to turn it into the free atoms, a carbon atom, 4 hydrogen atoms, and 4 oxygen atoms. And so in order to do that, when I take these 2 reactants and I break them apart into their component atoms, that costs me 2,642 kilojoules, all right? Because 4 times each one of these bonds, which is 413, and 2 times each one of these bonds, which is 495. All right, so that's the energy consuming part of the process. So now I've got all these atoms, and what I'm going to do is I'm going to take these atoms and I'm going to build products with them. Okay, So when I take those atoms and I build a carbon dioxide molecule, so I take the carbon and I take 2 of those oxygens and I build a carbon dioxide, that releases 2 times negative 799 kilojoules, because each one of those carbon-oxygen double bonds releases 799 kilojoules. But I'm also going to produce 2 water molecules. So the other 2 oxygens and those 4 hydrogens combine to give me 2 water molecules. And so each one of those water molecules releases 2 times 463 kilojoules of energy, so a total of 4 times 463 kilojoules per energy. It's negative because it's releasing that energy, okay? So overall, that's a negative 3,450 kilojoules of energy. And so then I just put those 2 numbers together. I add the 2642 to the negative 3450, and then the difference there is the energy release or the energy change of the reaction. In this case, it's a release because it's a negative number. But the overall energy change for this reaction is negative 808 kilojoules. So this should look pretty familiar. This is basically what we did when we talked about Hess's law. But in this case, the reactions that we are using and adding together are the reactions where we take the reactants and we just break it apart into its component atoms. But then I take those component atoms and I build the product molecules out of those. So very similar to what we learned when we talked about Hess's law. Okay, so that's conceptually, or in a picture way, hopefully you understand what's going on. Now let's just talk about how to use that equation that we learned a couple slides ago. So this was the reaction and this is our table. Now we just use that equation where the delta H, an estimate of the delta H of the reaction is the sum of all the bonds that we're breaking. So 4 times the CH bonds plus 2 times the oxygen double bond minus, straight from the table, 2 times the CO double bond value plus 4 times the oxygen hydrogen single bond value. So I just look up those numbers from the table. The 413, there it is. The 495, there it is. The 799 comes there. And the 463, and you just plug and chug at that point and you get the negative 808 kilojoules per mole. So you may be wondering, do you need, in the previous graph, we showed that as a negative 799 and that was a negative 463. So when you pull values from the table, do you need to make them negative if you're forming those bonds? No, that's what this equation does for you. It's built into the equation. So that negative in the equation is what converts all your table values into negative values. So don't worry about doing that. Okay, so that's one example. So now let me just do another example. Oh, and by the way, you have this equation on your equation sheet. You don't need to memorize it. You just need to know when to use it and how to use it. So now we're asked to calculate the delta H of the reaction for the following using those table values from table 8.3. I'm just going to get it set up and then we'll let PowerPoint kind of take over. Okay, but if you take a look at what's going on here, what bonds are we breaking? Well, this is a triple bond between the 2 nitrogens, so I'm going to break that. And I'm going to break 3 hydrogen-hydrogen single bonds. So this is going to be the sum of 1 times the nitrogen-nitrogen triple bond. Oops. Okay, and then we're going to add to that 3 times the bond energy for the hydrogen-hydrogen single bond. Okay, and then we're going to subtract from that the total of all the bonds that we're forming. We're forming 2 times, there's 3 nitrogen-hydrogen single bonds in here. 1, 2, 3, so 3 times 2 is 6. So 6 times a nitrogen-hydrogen single bond. So I'll just go to that table and I look up the value for these 3 bond types and I plug those into the equation. Okay, so if you do that, you find that I kind of did it in 2 steps here. So the nitrogen-nitrogen triple bond and the 3 hydrogen-hydrogen single bonds have those values, 941 and 436. And so that adds up to 2249 kilojoules. Okay, and so then I'm going to subtract from that the sum of all the bonds that I'm forming, the delta H of the bonds that we're forming. So there were 6 nitrogen-hydrogen single bonds, so 6 times 388 kilojoules, so that's 2328. And so the 2249 minus the 2328 gives you a overall estimate delta H of the reaction of negative 79 kilojoules. All right, so another type of question that you could be asked is something like this. So it says to draw a valid Lewis structure to determine the approximate nitrogen-nitrogen bond strength for this formula, N2H2. And you're given the bonding arrangement. Since it's not obvious which atom is going to be in the middle. You're given the bonding arrangement here: hydrogen, nitrogen, nitrogen, hydrogen. And then you're asked to use table A3 to get the bond strength. So the first thing to do is to draw the Lewis structure. Okay, so once again, we're just going to go through the step by step. So the number of valence electrons for this formula in this compound, you have 5 for each nitrogen, and there's 2 of those. And then there's 1 for each hydrogen, and there's 2 of those. So it's a total of 12. Okay, and so now we're told that the bonding arrangement is hydrogen, nitrogen, nitrogen, hydrogen. And so the next step says, well, the first thing you want to do is connect all those atoms together with single bonds. So that's how you would do it in this situation. Okay, and so that used up 2, 4, 6 electrons. So I have used up 6, so I have 6 electrons left over. And so the next thing it says to do is to give the perimeter atoms their octet. But remember, hydrogen doesn't want an octet. It's happy with just 2. So I'm going to go ahead and give the perimeter atoms these 6 electrons, so 2, and then it gives that one an octet, so 2, 4, 6, 8, and I still have 2 more electrons to place, so I'll just go ahead and put them on this nitrogen. Because so you see what I did there? These 6 electrons went here, here, and here. Okay, so the hydrogen's happy, that hydrogen's happy, this nitrogen's happy, it has 8. But this nitrogen's not happy yet. It does not have an octet. It only has 2, 4, 6. Well, remember how we deal with that. We can convert one of the lone pairs on an adjacent atom into a bonding pair. All right, so that would convert the structure into this. You have hydrogen, nitrogen with the lone pair, but now with the double bond to the other nitrogen. Okay, and so now everybody's happy. The hydrogen has 2, it's happy. Hydrogen has 2, it's happy. This nitrogen has 2, 4, 6, 8. This nitrogen has 2, 4, 6, 8. So everybody's happy. So now this is the key thing. So now I would go to table 8.3 and I would see what is the bond energy of a nitrogen-nitrogen double bond. Okay, so you get the Lewis structure, you just look up the value in the table, and you see that it's 418 kilojoules per mole. Okay, so now there are a couple trends that we want you to learn regarding bond strength. So it's based on 2 factors. So first of all, it's based on the distance between the 2 nuclei. Okay, and also it's based on the bond polarity, or you could think of it as the difference in electronegativity between the 2 atoms that are bound together. Okay, so distance between the 2 atoms, or the difference in and the difference in electronegativity between the 2 atoms, or another way to think of that is the bond polarity. Okay, so we'll focus on distance first, and then we'll talk about the bond polarity. So regarding distance, and we've seen this already when we showed the slide regarding the bond order, how the single bond compared to the double bond compared to the triple bond. Because what we see is that bonds get stronger as they get shorter. So remember that the double bond was shorter than the single bond, and the triple bond was shorter than the double bond. Well, that's true just in general. So bonds get stronger as they get shorter. So we'll look at a couple examples. So first of all, in this table, we're going to look at hydrogen-hydrogen single bond versus a chlorine-chlorine single bond. So first of all, I'll show you the lengths of those 2 bonds in picometers. Picometer is a trillionth of a meter. There are a trillion picometers in 1 meter. So the bond length for the hydrogen-hydrogen is really small, 75 picometers. But for chlorine-chlorine, it's larger, 200. And so compare the energies of those 2 bonds, okay? We've said that as they get shorter, they get stronger. So I'm going to predict that the hydrogen-hydrogen bond is actually stronger than the chlorine-chlorine bond. And it is. So the bond energy for hydrogen-hydrogen is 436. For chlorine-chlorine, it's only 243. Okay, so the trend holds true when you're looking at single bonds that are different lengths. This one we've already kind of talked about, but let's just get it in our notes as well. And this is with a different bonding situation. So you can have a carbon-oxygen single bond, or you can have a carbon-oxygen double bond. And so the lengths of those 2 bonds are this: 143 for the single bond, 123 for the double bond. And so how does that change the bond energies? Well, I'm going to predict that the carbon-oxygen double bond is going to be stronger because it's shorter. And it is. Okay, so the bond energies there are 358 for the single bond, 743 for the double bond. Okay, so these 2 examples just confirm the bonds get stronger as they get shorter. Okay, so in the next slide, we'll talk about how bond polarity affects the bond strength. So here it is. The bond polarity has an effect such that the bonds get stronger as that electronegativity difference gets larger. Okay, so the example we'll look at here is this. So carbon-oxygen double bond, so that has a certain electronegativity difference, versus a carbon-nitrogen double bond, which has a different electronegativity difference. So you remember, you can just look up the numbers in a table of electronegativity values and subtract the two numbers to get that electronegativity difference. For oxygen, it's 3.5, so that has an electronegativity value of 3.5, but then the carbon has a value of 2.5, okay? So when you do that, the difference is 1, and you'll see that the difference comes up for the carbon-nitrogen right now. So its difference is only 0.5, okay? And then I'm gonna say, based on this trend, that because this difference is larger, then this bond strength is gonna be larger. And it is 743 versus 615. So the larger the difference in electronegativity, or the more polar the bond is, the stronger the bond is. Okay, so we'll stop there. So what we talked about today should enable you to do questions 14 through 18 in your homework assignment, and do questions 45 through 61 in the extra practice, and then some good tutorial videos.